So we're going to talk about kinetic molecular theory. We just spent a lot of time going over a lot of gas laws, some simple gas laws, the ideal gas law, Dalton's law of partial pressures, etc. Laws describe what happens. Theories explain why those things happen. So kinetic molecular theory explains why the gas laws are what they are. And this is the simplest model for the behavior of gases. Kinetic refers to motion. My pointer working. Kinetic refers to motion. Molecular refers to molecules. So this is a theory about gases based on the movement of the molecules or particles. So here we're thinking about a gas as a collection of particles in constant motion. And so these particles are moving, and they're going to bump into each other, and they're going to bump into the container. The first premise of kinetic molecular theory is that the size of a gas particle is negligibly small. That means it's so small that we don't have to consider how big it is. So we're assuming that gas particles are not occupying any volume, although they do have mass. Now, do gas particles have volume? Of course they do. But there's so much empty space between the particles that the actual size of the particles doesn't matter. Example here, at standard temperature and pressure, argon atoms only occupy 0.01% of the gas volume. So to put this into terms we can relate to, if an argon atom was the size of a golf ball, the nearest neighbor would be 4 feet away. In that 4 feet, in that 4 feet between those two golf balls, there's absolutely nothing. It's empty space. Okay. The average kinetic energy of the gas particles is directly proportional to the temperature in kelvins. Now, as with the other gas laws, we always talk about gases in terms of kelvins because the Kelvin scale does not have any negative temperatures. Average kinetic energy is one definition of temperature. So the temperature of a substance is a measure of the average thermal kinetic energy of the particles in that substance. So this statement means that directly proportional, when we raise the temperature, the average speed of the gas particles increases. So higher temperature, the gas particles are moving faster. Now, when we're talking about solids and liquids, especially solids, the particles are fixed in place, and so when you raise the temperature, they just vibrate faster. But gas particles are actually moving through space. And so when you raise the temperature of a gas, the particles are moving faster. They're zinging around faster in that container. It's important to understand that here we're talking about the average kinetic energy, the average speed. Not all gas particles move at the same speed in a given sample. There's an average. Okay, just like, scores of students in a class are not all the same, and just about everything that you can think about in terms of humans, you can talk about averages, but they're all different, right? So the collision of one particle with another or with the walls of the container is completely elastic. And that's a physics idea. When you have an elastic collision, two things collide, energy may be exchanged, but there's no loss of energy. I think we have a picture of that. Yeah. So in an elastic collision, the total kinetic energy of the colliding bodies remains the same. In real life, there are very few truly elastic collisions. Most collisions involve some loss of kinetic energy due to heat. Probably the closest thing we can come is like a billiard ball. And even these are not perfect, but you roll two billiard balls at each other, and they have kinetic energy. When they hit, energy may be transferred, but the balls roll away with about as much kinetic energy as they came in with. Now, sometimes the one ball will almost stop, and then the other one will go off faster. That's in contrast to an inelastic collision. If you were trying to play pool with billiard balls made out of clay, when they ran into each other, they just go thunk, and nothing would bounce off, right? Because they're soft and they'll absorb that impact, the kinetic energy gets turned into heat. Any questions? So we can use kinetic molecular theory in the slides. It's often abbreviated KMT because it's an awful lot of letters to type out all the time, to explain a lot of things that we observe about gases. We can explain gas pressure and why gases exert a pressure. So the gas particles are constantly moving, and they're going to strike the sides of the container with a certain amount of force. That amount of force is going to depend on how fast they're moving and how massive they are. But the result of many particles in a gas sample striking the surfaces around them is going to give us a pressure. Remember, pressure equals force divided by area. So you can look at the inside of the container. It has an area. You have particles hitting the inside of the container with force, and so you have a force divided by area. The gas exerts a pressure on the container. We can explain Boyle's law. So the volume of a gas is inversely proportional to the pressure. That is one way to state Boyle's law. So looking at the volume, if we decrease the volume of a gas, that forces that same number of molecules into a smaller space, right? Now the area that the area of the inside of the container is smaller, and not only that, but the particles are going to hit the sides more frequently because the container is smaller. Does that make sense? I sometimes think about, you take a room full of kindergartners, and, they're ready for recess, so they're all just kind of jumpy, and they're running around the classroom, right? So they're going to bump into each other. They're going to bump into the walls if they're just, running crazy like 5-year-olds do sometimes. If you push all of them into half the classroom and pull out one of those dividers, you've got the same number of children running in the same crazy way in half the area, they're going to run into things more frequently, right? It just kind of makes sense. So that's the same thing that happens with gases. So in Boyle's law, we see that if you decrease the volume, then you increase the number of collisions, and so the pressure will increase. So you make the volume of the gas smaller, the pressure goes up. That make sense? So Boyle's law said what happens. Kinetic molecular theory helps us to understand why that happens. Charles' law says the volume of a gas is directly proportional to the absolute temperature. Well, kinetic molecular theory says we increase the temperature, then the average speed of the particles increases, right? This is typed out nicely in a later slide, but I'm going to write it out here too. Kinetic energy equals 1/2 mass times velocity squared. We're not actually going to do calculations with that, but that's just to help us to understand what's going on with kinetic energy. So if the mass of the particles is going to stay the same, but when we increase the temperature, the velocity will increase. They move faster. So if the velocity increases, the kinetic energy increases, or if the kinetic energy increases, the velocity increases. They're tied together. So we've got these particles moving faster, but when we look at Charles' law, the pressure has to remain the same. So if we've got these particles moving faster, that's going to increase the pressure, right? Because they're going to hit the sides more forcefully and more frequently. So in order to keep the pressure the same, we have to let the volume expand so that we can keep the pressure the same. So the volume of a gas is directly proportional to the temperature. If you increase the temperature at the same pressure, the volume must also increase. Did that make any sense? I got a couple of nods and no shaking of the heads, just blank stares. So we'll go on. Avogadro's law. volume of a gas is directly proportional to the number of gas molecules. So if you increase the number of gas molecules that are in the container, it makes sense that those particles are going to hit the sides more frequently, right? So if you put twice as many kindergartners in that classroom, they're going to run into each other more frequently. The pressure would go up. Well, in Avogadro's law, we're also maintaining a constant pressure. In order to do that, we have to expand the volume. So if you increase the moles of gas, you increase the volume. Dalton's law of partial pressures. If you have a gas mixture, the total pressure of the mixture is the sum of the pressure from each of the individual gases. So kinetic molecular theory tells us that the particles have negligible size and they do not interact with each other. When they collide, they just bounce off elastically without any loss of energy. Particles of different masses are going to have the same average kinetic energy at a given temperature. How can two particles that have different masses have the same kinetic energy? Kinetic energy is 1/2 mass times velocity squared. If the kinetic energy is the same and the masses are different, what else must be different? The velocities. So you can have gases of different size molecules that have the same average kinetic energy. All that means is that some of them are moving faster. The small ones are moving faster than the large ones. Because the kinetic energy is the same, the total pressure of the collisions is the same. So it doesn't matter if one gas is krypton and one gas is helium. At the same temperature, they have the same average kinetic energy, and it's the kinetic energy that affects the pressure, not the size of the particles. Does that make sense? This negligible size business. So I live in Reedley, where fruit packing and fruit growing is like the major thing going on. So you see big trucks full of fruit, sometimes full of nuts, but mostly fruit. And they have to come into the scales and weigh before they can go off and go trucking across the country, right? So let's imagine, I think they might still be doing nectarines. So big truck of nectarines pulls onto the scale, and they weigh it and they record it and everything. And then somebody comes up, hey, you dropped this one nectarine, and toss it up onto the truck. Do they need to reweigh the truck because of the one nectarine? No. Because compared to the weight of that truck, which would be in tons, right? One nectarine doesn't matter. Does that mean the nectarine doesn't have any mass? No, it has mass. It's just so tiny in comparison to the whole thing that it doesn't matter. That's what we're talking about with the negligible size. Compared to the size of the volume of the gas that it occupies, the size of each individual particle just doesn't matter. Any questions? So kinetic molecular theory predicts behavior that's consistent with our observations and measurements of gases. And just as a reminder, scientific theory is the most powerful kind of scientific knowledge. This gives us the most understanding of what's going on. Now, the model does break down under certain conditions, but when we look at those conditions, it helps us to understand further what's going on. So the average kinetic energy of gas molecules depends on the mass and the average velocity. So that's what I've been writing over and over again, which, in retrospect, I should maybe just put that on the slides. Kinetic energy is 1/2 the velocity, mass times the velocity squared. So if they all have the same kinetic energy, different masses, they must have different velocities. So the kinetic energy can be the same. So we have to talk about averages here, and this gets into some weird math that we don't really want to talk about. So what we talk about here is the root mean square average velocity. and that's URMS. It is a special kind of average. It's close to a simple average, but it's not. So just think of that as the velocity, average velocity. So the average kinetic energy of a gas sample is equal to 1/2 the number of molecules times their mass times that average velocity squared. So 1/2 mv squared, basically. So in a gas mixture, at a particular temperature, lighter particles are going to travel faster than heavier ones. Right? Let's go back and look at this. So if the mass is bigger, then the velocity must be smaller in order to have the same kinetic energy. So it's football season. Been going to a lot of football games. So I'll use the football analogy. So you've got the running back and you've got the lineman. So on my son's football team, he's one of the running backs, and he weighs maybe 175, and he's pretty fast. And then there's this other guy, and he's just awesome. He weighs 360 pounds. I mean, he is massive, and he's the center, and he's awesome on the line. So you've got the small guy and the big guy. If they're going to run a race, who's going to win? The small guy, right? Because he moves a lot faster, right? Small gas particles move fast. Large gas particles move more slowly. Okay? They may have the same kinetic energy. You can think of it this way, too. So big guy, for him to knock you down, is going to require a certain amount of force. He's not going to have to go very fast to have enough kinetic energy to knock you over. The smaller running back is going to have to run at you with greater speed in order to hit you with enough force. Does that make sense? So large particles are slow, think the big football player, and the small particles are quick. So the average speed of gas particles depends on their size. And so we can derive the equation, but we don't want to. So here's just the equation. The average velocity is equal to the square root of 3RT over script capital M. There's way too many M's, right? So 3 is just the number 3, so that's nice. We needed something simple on Monday morning. R is the ideal gas constant. But we're going to use different units on the ideal gas constant. Okay, so that means the number's different. It represents the same value, just like 1 foot describes the same length as 12 inches, right? Just different units. So this is 8.314 joules per mole Kelvin instead of liter atmospheres per mole Kelvin. And here, capital M here is the molar mass, and it must be in kilograms per mole in order for the units to all work out. So let's do an example. Calculate the root mean square velocity of gaseous xenon atoms at 25 degrees Celsius. So our equation is the root mean square velocity equals, that's supposed to be an equals, the square root of 3. That's not a 3, that's an R. I got a new tip on my stylus and it's giving me fits. 3RT over this funky M. So R is the ideal gas constant, but for this equation, I'm blanking. 8.314. No, you actually don't, because I have a hard time with it. 8.314. I knew there was an 8 in there somewhere. That's not a 3, that's an 8. See, I was doing it. 8.314. No, I'll give you that one. And the units are joules per mole Kelvin. And then we need the temperature. As with all gas calculations, the temperature has to be in kelvins. So it's given to us in Celsius, and so we have to convert it to kelvins. And then we need the molar mass of xenon, and it needs to be in kilograms per mole. So for xenon, all we have to do is look at the periodic table. periodic table tells us it's 131.3 grams per mole. But we need that to be kilograms. So we have to convert that. You may or may not need to do this all written out like this. So I want kilograms. I want to get rid of the grams. 1 kilogram is 1 times 10 to the third grams. And so this is 0.1313 kilograms per mole. So I'm going to put these numbers into the equation. I've got 3 times 8.314 joules over mole Kelvin times 298 Kelvin. And all of that is divided by 0.1313 kilograms per mole. And then the square root of the whole mess. So I'm going to do the math first, and then we're going to talk about the units. So on my TI-36X Pro, I put the square root sign in first. And then I do 3 times 8.314 times 298 divided by 0.1313 equals. And I get this number, 237.92, and it just keeps going on and on. Well, for significant figures, after I convert my temperature to Kelvin, I've got 3 significant figures here. That one's got 4, this one's got 4, so we should round this to 3. And it's going to be 238. But then we need to know what the units on that are. What do you think might be a unit for velocity in the metric system? Meters per second? It is meters per second. So you can remember that, but I'll also show you what's going on here. So we have joules per mole Kelvin times Kelvin divided by kilograms per mole and the square root of that. So the kelvins cancel and the moles cancel, right? We end up with joules per kilogram, the square root of that. I think most of you will follow me there. Well, the joule is a name for another unit. It's a short name, basically. So joule is energy. Energy is the capacity to do work, which is a force times an area. So a joule is equal to a Newton meter. A Newton is a unit of force. A Newton is a kilogram meter per second. Let me get this right. Yeah, kilogram meters per second squared times meter. And so a joule is equal to kilograms meters squared per second squared. So when we put that into here, kilogram meters squared per second squared divided by kilograms, taking the square root of that, the meters don't cancel out, the kilograms cancel out. We end up with the square root of meters squared per second squared. That's where the meters per second comes from. If you like that, awesome. If you don't like that, just remember the velocity ends up in meters per second. But this is why we need to use kilograms for the unit in the molar mass for that one. Any questions? I'll give you this equation as well. So I'll give you the equation and I'll give you this value of R. You need to remember, though, that that funny M is the molar mass in kilograms per mole. So we talked about the differences between lighter molecules and heavier molecules. They have different average average velocities at the same temperature. But the way that average is distributed looks different too. So here we have oxygen with a molar mass of 32 grams per mole, and here's hydrogen with a molar mass of 2 grams per mole. And these guys in between, from oxygen to hydrogen, are decreasing in molar mass. So the size of the particles is getting smaller. And we see that the distribution of molecular velocities for oxygen is much narrower than it is for hydrogen. So this green one out here is very spread out. And so the average temperature for hydrogen is higher at this temperature than it is for oxygen, but it's also more spread out. Come on. When we change the temperature, so that is variation of velocity with molar mass at a particular temperature. When we increase the temperature of a particular gas, we also see that the distribution spreads out. So this is a single gas at 273 Kelvin. As we increase the temperature to 1,000 Kelvin and 2,000 Kelvin, the average molecular velocity increases, but the distribution spreads out. So now we've got this wide distribution of velocities, much larger than at a lower temperature. So the average is larger here, but also the particles with the highest velocities are a lot higher than down here.